The amounts of automobile losses reported to an insurance company are mutually independent, each loss uniform between 0 and 20,000. The company covers each loss subject to a deductible of 5,000. Calculate the probability that the total payout on 200 losses is between 1 and 1.2 million. So the loss is given to be uniformly distributed. Let the loss be X and let the payout be Y. So it's uniformly, the loss is uniformly distributed on 0 20,000. So f of X is 1 over 20,000. And Y is the payout, which is 0 when the loss is less than 5,000 because of the deductible of 5,000. And then if the loss is bigger than 5,000, the payout is X minus 5,000. X is the loss, remember? So we start by finding the mean and standard deviation of each payout, because look, we have to find the probability that the total payout on 200 losses. So we are interested in total payout on 200 losses. So for this, we start by the payout on each loss. So the payout is Y. So we need the mean and standard deviation of each payout. And mean of Y is the expected value of Y, which will be the integral of Y against fx dx. And remember, we've done this a few times a bit earlier, where I explained that in general, E of Y should be Y against Fy. But since Y is going to be changed in terms of X, and we have to do that because we know the PDF only of X, where we don't know the PDF of Y. So therefore, we have to change the Y into X, and therefore we'll be integrating it against the PDF of X. So we have that. So the only non-zero part will be when X is bigger than 5,000. So X, so we don't really start from negative infinity, but we start from 5,000. And then we don't go all the way up to infinity because X stops being non-zero after 20,000. So we go, so the only non-zero portion of this integral will be between 5,000 and 20,000. And that's when Y is X minus 5,000. And the PDF is 1 over 20,000. And the integral of X minus 5,000, you can just use power rule on X minus 5,000. So it'd be X minus 5,000 squared by 2, and the 2 gets multiplied with this to get 40,000. And if you don't like using power rule, you can do your U substitution. It will lead to the same thing eventually. So after you substitute the 20,000, you get 5625. The lower limit when you substitute 5,000, 5,000 minus 5,000 is 0. So the mean of Y comes out to be 5625. Now we need the standard deviation of Y, but for standard deviation, we first need expected value of Y square, because remember, eventually standard deviation is the square root of variance, and the variance is E of Y square minus EY whole square. And so expected value of Y square is done the same way. Now you integrate Y square against Fx. And Y square would be X minus 5,000 squared, where it's non-zero, same limits as before. And this one ends up being this cube over 3, and 3 times 20,000 is 60,000. And then you substitute the limits. And then E of Y will be standard deviation of Y will be the square root of EY square minus EY whole square. So EY square is this 5625,0000. And the EY we found earlier was 5625. And so you get 4961. Now we have more than 30 payouts. We have actually 200 payouts. And the central limit theorem applies. Let T denote the total payout on 200 losses. Then remember, the central limit theorem, the mean of T will be n times the mean of each, and n is the number of losses in this case, or the number of payouts. So it'll be 200 times the mean of each payout. And I mean, the total mean of 200 payouts will be 200 times the mean of each payout. And then standard deviation of the total payout is the square root of n, or the square root of 200 times standard deviation of each payout. Yeah, that's central limit theorem. We've done that a few times in the earlier problems. And the next step, since we need the probability that the total payout of 200 losses is between 1 and 1.2 million. So the next step is to change the 1 and the 1.2 million into z-scores, because we have to use the tables which are given in terms of z. So the z-score of 1 million will be 1 million minus the mean over standard deviation. And these are the total losses. So the mean of total losses will be used, the 1125000 in this standard deviation. And that ends up being negative 1.78. Similarly, the 1.2 million ends up being 1.07. And therefore, the probability of t between 1 and 1.2 million is the same as z between negative 1.78 and 1.07. So that's equal to probability of this minus probability of this. And you know that to use the table, we have to have probabilities in the less than form. So this one is fine. And also we need to have them as positive, the z's as positive, to use the table. So probability of z less than negative 1.78 is the same as probability of z bigger than 1.78 by symmetry. And then we keep this one, and then again this inequality is going the wrong way, so we change it into 1 minus probability z less than 1.78. Now strictly speaking it should be less than or equal to 1.78, but you know, in continuous distributions it makes no difference whether you include the equals or not. And now the 1.07 from the table, let's open up the table. So the 1.07 from the table is 0.8577. 0.8577, and the 1.78 is 0.9625. And then after substituting these, you get 0.8202. And now choice D is 0.8201, and that's the correct answer. The little difference we see is because of the rounding. And also, they sometimes try to interpolate and be very accurate. They tried more decimal places, but actually the answers are always wide apart, so that using z up to 2 decimal places should always land you into the correct answer, even if you are a little bit off because of rounding. So the correct answer is D then, and that ends it.